Okay, let's get going. I teach 2100 right before this, so my lectures are, I'm always thinking about circuits when I walk in here. It's hard to get connected. But anyway, we'll talk about the Gaussian beam today. So we're going to go through an awful lot of stuff. I'm going to kind of derive the Gaussian beam. And I don't think the derivation is very important, but there's a lot of parameters that are going to come out of it. We're going to introduce Z naught and Q of Z and omega and radius and stuff. So there's a lot of definitions that are going to happen today, and we will use these again and again. So don't feel lost if you don't get them right away. I'm going to derive it. We'll show their basis, and then we'll create some formulas which use them in the purpose. But I want to define a bunch of terms today. So we were talking on Friday about just kind of the fundamental aspects of the field, and we said the electric field of a laser beam is basically like a plane wave. So we said it's got some amplitude, it's got some function which gives it an XYZ shape, and then it propagates, let's say it's going in the Z direction, so J, K, Z, minus. So it's planar in terms of propagating like a plane wave, but it's got some limitation. We know it doesn't extend to infinity, it's only finite in width and stuff. Maybe it's got some curvature. So that's what this function here is. And our goal is to figure out this function. So we plug that into the wave equation. So we plug that into del squared E plus K squared E equals 0. And we took out all the redundant terms, and that took us to an equation of this form. Del squared transverse psi minus 2 jk d psi dz equals 0, where del squared transverse is just d squared dx squared plus d squared dy squared. So we started with something like this, plugged in the wave equation. Now we have a new equation. This is an equation for psi. So it's no longer an equation for E, it's an equation for this crazy envelope. So now we have to solve that. And so that's the goal of today. So we're going to assume a basic form of this. First I'm going to do a couple of things. I'm going to assume we've got a cylindrical beam, so I'm going to use cylindrical coordinates instead of x, y, and z. So this would be written in terms of, this would look like 1 over r d dr r d psi dr minus j k 2 k d psi dz equals 0. So same equation, just in radial component, cylindrical terms. Now, I know we talked about this before, that this beam propagates, it's fairly collimated, and it doesn't diffract in a way which changes its shape. We know Gaussian beams diffract into Gaussian beams, so let's assume it's a Gaussian beam. So we're going to look for a Gaussian solution, just as our trial. And remember, the truth in all differential equations, when you got to solve one, if you can guess the answer, you win. You know, there's only one answer to this thing. So we're going to guess an answer and see if it comes out close. So we're going to try this. We're going to say, let's try looking for a solution of this form. And it's going to be an exponential. And I'm going to throw this thing in here, j p of z, some function of z. I don't know what it is. Just kind of a safety valve in case something comes up. And then plus k r squared over 2 q of z. Okay, probably not your first choice in assuming a solution. So what's going on here? And I have a funny feeling this was not the first choice the original people did either. I suspect it's all kind of, we got to add terms. But anyway, what we have here is I've got a e to the j k r squared. So this e to the r squared is my Gaussian term. And I'm expecting both a Gaussian amplitude and a Gaussian amplitude to be something of the form e to the minus, say, r squared over some constant. Let's call it omega naught squared. That would just be a real term, and it would have some sort of shape like that. But I'm also expecting this wave front, as it propagates, to maybe have some curvature. And so as it's traveling along, maybe it's a plane wave here, but I suspect that it might start to diffract and get a little bit of curve. We talked about that on the first day, in fact, how there's a little bit of curvature. And so this curvature also might be nicely described by an e to the j k r squared over some sort of radius of curvature or something. So the reason I have a q parameter here instead of an imaginary, I've got this thing here. I've got j times kr squared over 2q, and I'm going to let q maybe be this dynamic thing, which sometimes it's real, sometimes it's imaginary. Maybe it will make everything work for me. So we'll try this. Now, I'll jump ahead a little bit. Of course, this is going to work. And you're going to find Q to be an amazing number. We're going to characterize all of our beams by Q. So one of the targets of today's lecture is what is Q? What is the Q parameter? How do we use it? And you're going to find when you're designing your cavity, Q is going to be the variable you develop. But here's where Q comes from. So we're trying to find this envelope function. We take this crazy guess like that, put it in. P of z, this is a j p of z. Maybe the phase changes a little bit differently than e to the j kz. Here I just assume I get every wavelength I get 2 pi phase. It's probably true, but maybe because it's curving and stuff, maybe it's getting just a little more, a little less, I don't know. So we're just going to throw that in kind of as a safety valve just to take care of any additional phase change. Hint, there's going to be a little additional phase change. So this will come up. But that's the goal. So we start with that. So what do? We take this trial solution, we plug it into our differential equation, and we see what happens. So we're going to convert. We took E, converted into an equation of psi. We take psi, and we're going to convert it into an equation of P and Q. And we'll try and solve those. So this is kind of this classic way you solve problems, is just kind of redefining, catch the gross behavior and try and find the details later. So I plug this into our differential equation, and you grind it around. And what you come up with is this. You're going to get k squared over q squared of z times q prime of z minus 1 times r squared minus 2k p prime of z plus j over q of z, all of this times psi equals 0. So that's what comes out of doing that. Now what's nice here is you see that I've got, this term depends on r squared, and this does not. And so r could go all over the place, and this equation must still be true. And the only way that can happen is if these are independently 0. That has to be 0, and that has to be 0. And that makes this thing very solvable all of a sudden. So because I'm multiplying by r squared, must be true for all values of r. The only way that's true is if this is 0 independently. Okay, so look at this. This is nice. I've got an equation and nothing but q in it. I want to set it equal to 0. I can do that if I assume that q prime of z minus 1 equals 0. Anybody want to guess what q is? This is not a hard differential equation to solve. What's the derivative of z? Yeah, the derivative of z gives you 1. So I immediately say, this is pretty cool. So q of z equals z plus some constant, some differential constant. Making progress. Now, let's just call that z naught. Or let's call it q naught. We don't know what the heck it is. Some constant. Now, this leads to a couple questions. What the heck is z? Where is z? Where is z equals 0? What does that mean? And what's this constant? How do we deal with that? So we will deal with both of those as we go along. Let's look at, let's think about this constant first. So I'm going to go to z equals 0 wherever that is. I don't know where it is, but I'm going to set z equals 0. And that gives me q equals some constant. And I'm going to plug that into my trial solution up here. And what I want to see what do I get out of this thing. So I'm going to get a e to the minus j times k r squared over 2 q naught. Now, I look at that and I say, is this what I want? Does this make sense? I'm looking for a beam which has a Gaussian profile. This is just a pure phase term, nothing else. It has no amplitude dependence whatsoever. It goes on forever. That's not what I expect. What I do expect is a Gaussian. So this suggests to me that Q naught must be imaginary. And if I let Q naught equal some J Z naught, so my Q has this complex term. When I plug that in, I get e to the minus j k r squared over 2 j z naught, where z naught is just some variable. It's a constant. I don't know what it is yet. But I like this a lot better because what happens is the j's cancel and I get e to the minus k r squared over 2 z naught. And that looks like a Gaussian. And I know I'm looking for a Gaussian solution. So now I can look at this and I can get some clue about what z naught is. Because I know a Gaussian has a shape. And here's, say, r equals 0. And at the 1 over e point, we kind of define some width. So let me just call this width omega naught. I don't know why we call it omega, but it's called omega. And that's a radius. You know, it's not like we don't have omega in frequencies and that kind of stuff, but for somebody, sometime, somewhere said, we're going to call this radius omega. So if I've got a Gaussian beam, its 1 over e point would be omega, and so that would be described as e to the minus r squared over omega naught squared. Okay, so I can compare these two. This, omega, is the physical radius of the beam. It's a real thing. I put the laser beam there, I see it's got a finite size. I can measure omega naught. This is what psi is telling me in terms of z, k, r, that. So I can look at these two and say, I now know what z naught is. I can relate z naught to a physical parameter. And so, by comparing those two, God, I hate these erasers. Okay, by comparing those two, we see that we would define omega naught squared is going to be equal to 2 z naught over k, which is lambda z naught over pi. Or we get z naught must equal pi omega naught squared over lambda. Now, that's a parameter we're going to use a lot. So there's z naught. It depends on the wavelength of the beam and basically the area of the beam. So I take a laser beam, it's got some area, divide by lambda, that's z naught. And I'll tell you what z naught refers to. It's a characteristic length, obviously. We start looking at the beam, we'll see what it all means, but it's going to be a parameter which you're going to get to know and love. It's called the confocal parameter, or the Rayleigh range. I've seen both terms here. Confocal parameter. Or the Rayleigh range. Okay, so anyway, there's one of the first terms we're going to define. So that just came out of Q. So remember, Q equals, now we know Q. Q of Z equals Z plus J Z naught. And Z naught is a constant, and it's completely defined by the beam we're looking at. Okay, now, let's see if we can make more progress. So, we've got all these other terms here. So, let me look at, well, I want to look at it right here. I've got this expression, e to the minus j k r squared over 2 q of z. I've got a 1 over q of z here. So let's see if we can rewrite that. 1 over q of z. I'd like to replace that if I can. And that's equal to 1 over z plus j z naught, and we can expand that. That's equal to z over z naught squared plus z squared plus, let me do this right here, minus minus j z naught over z squared plus z naught squared. Just simple complex, putting the real and imaginary terms. I'm going to replace this 1 over q of z with this. I'm going to write it into that, and we're going to ignore p of z for a while. So what we get when we do that is a more full description of what the field looks like everywhere according to this silly analysis we've done. And so you do that and you say, well, psi of x or psi of r equals, you've got this exponent times minus k naught r squared z naught over 2 z squared plus z naught squared. And then an exponent of minus j k r squared z over 2 z squared plus z naught squared. So that's just, I've taken q out and just put it in terms of its z and z naught. Now notice the first term is real, the second term is phase. So this is clearly going to be some sort of Gaussian. When I plot it like that. And it's going to be r squared over the spot size. So I'm going to compare this whole mess to e to the minus r squared over, let's say, omega of z. So now z is no longer 0. I did the z equals 0 initially. Now we're off just in random z space. And so this is a Gaussian. So it must have some shape like this. And comparing this form to this, my 1 over e point must be embedded in all this crap here, right? So I'm going to solve for the spot size as a function of position by extracting all that stuff out of here. And what we get when we do that, so there's a lot of rich stuff falling out of this today. You're going to get a lot of formulas which are going to be useful. Okay, so we pull all the junk out and we'd say, well, comparing the real term here with the expected spot size, we get omega squared as a function of position. So the radius of the beam as z increases is given as, I got it here, that's going to be this 2 z squared plus z naught squared over k naught or kz naught. And I stir this around and play around. And what this becomes is omega naught squared, do it in terms of z naught, times 1 plus z over z naught squared. And that's my final answer. So this says the size of the beam is going to grow as z increases. And if I were to plot that, notice this quadratic, it squares, so it's always positive. So if you make it a plot of your beam size, here's z-axis, here's 0. I would find the beam kind of following a curve like this. Where this is omega of z, and this is omega naught. And this is z equals 0. So all of that is just falling out of this equation. So what do we see? We see we have a beam. At z equals 0, it's minimum. And then as it propagates, it starts to grow. How fast does it grow? Well, it depends on z naught. If z naught is a big number, it's not growing very fast. If z naught's a small number, it's exploding. And remember, what was z naught? Z naught was the area of the beam divided by lambda. A great big area means z naught's big, means it doesn't grow very fast. Remember, diffraction, a big beam doesn't diffract very fast. A small beam does. Hey, this is all looking pretty consistent here. So we have that. The waist is right here. We call this the beam waist. So another term you're going to get to know and love. Beam waist. This laser beam comes in. It reaches a minimum and no smaller. Then it starts spreading again. I can try and focus it tighter. I'll take a lens, I'll bring it out, I'll focus it in. It's going to come down, it's going to reach a minimum someplace and expand again. It never goes to zero. You know, rays cross, these never cross. This thing comes in, blows back up. So a laser beam has the smallest it can get is called the beam waist. And you think about it, if you know about your diffraction, you know, if you take lenses, the best you can do is half a wavelength kind of thing. It's effectively the same thing. The laser beam can come down some number of wavelengths is as small as it's going to get, depending on how tightly you focus. But however, whether it's a collimated beam or whatever, the laser will come along, at some point it reaches this minimum, and we call that the beam waist, and then it starts expanding again. And so the beam waist is where we define z equals 0. Where was z equals 0? It's where the beam has reached its minimum. That is defined as 0. And then from that, we march on out. So now from this q parameter, we've learned, you know, q equals z plus jz naught. If I tell you q equals 100 plus 10j, I've basically told you everything I can tell you about that beam. I've told you where the waist is, I've told you how big the beam is, and now you can predict how big it's going to be as it propagates. In fact, when I was in grad school, we bought this argon laser, and I was quite impressed by it. And in the spec sheet, it says the output beam, Q equals blah, blah. It didn't tell me the size of the beam, it didn't tell the rate, it just said Q is. And with that, I knew everything I could possibly know about this beam. So this is an incredibly rich number. You had a question? You did, yeah.
In our psi function up there, we expanded Q to Z
Yeah.
What happens to the P of Z term?
We're blowing the P. We're not worried about P of Z yet.
Okay.
We'll get to that in a minute. But it was, you know, there is a P of Z term out here. But remember, when we expanded this thing out, we had 2 terms set to equal to 0, and we had a Q term, and then we'll have a P term, which also went to 0. So we're just looking at 1 right now. Yeah, we'll get to that in a minute. So anyway, so I want to pound in the head. Q, big number. We're going to use Q a lot. It looks very simple there. Z plus a complex number. But those 2 numbers represent just about everything we could possibly know about this thing. I have to tell you the wavelength. That's the other thing. If we give Q, and then I say, and the wavelength is, okay, now you know pretty much everything there is to know about this beam. So that's that. Beam waist. Comes to tight focus. If you plot this out, it looks almost collimated here. It's just kind of cruising right along, and then it finally starts to spread. The place where the area doubles is going to be when I get to Z is equal to Z naught. So what's Z naught? Z naught is out here, let's just put it right here, where this is 1.44, what that was. The area of the beam has doubled at Z naught. So Z naught is a physical distance. It's a number. You know, let's say I said it's 10 centimeters. So I've got a waist here. 10 centimeters away, the beam will have doubled in area. That's what that means. We call that the Rayleigh range of the confocal parameter, because from minus Z naught to plus Z naught, the beam is roughly collimated. After that, it's spreading. But in that zone, at near 0, 0, plus or minus Z naught, the beam is at its maximum intensity. And so if you're trying to image something, you know, you're trying to get really down, that's where your focus is going to be. Or if you're trying to get a lot of high intensity, for example, I want to extract a lot of gain out of a laser gain medium, I will put my gain medium inside this zone here, and then I've got the maximum intensity for stimulated emission. If I put it out here where the beam is really big and large, I don't have as much intensity, so my stimulated emission is less. So my confocal parameter gives me some sense about how large I can make my laser crystal and all that kind of stuff. So that's what the confocal parameter corresponds to, is over what distance does this thing remain collimated. And how do I know that? Because this formula here, I can see the spot size is defined in terms of my random position and z naught. And so it just falls right out of there. Yeah?
Wait, so is omega squared z, is that a function of area of the beam?
This, well, if I multiply, we'll get into that. It's actually, this describes the radius of the beam. The area of the beam, turns out, we'll get to that later. The area of the beam is pi omega squared of z over 2. Why over 2? Because we're going to define the effective area of the beam. We're going to integrate this thing, and we're going to effectively define it in terms of its intensity. And the intensity falls off pretty rapidly when you go to E squared. And so we effectively, you know, if you say that's the size of the beam, you don't have your total intensity. You're overestimating your intensity. We'll talk about that later. But you know, basically we define our intensity as an integral of E squared dr. And so that's where it comes out of 1/2. Don't worry about that though. But it's, you know, it's effectively the area of the beam. But we use this for the beam radius.
Okay.
So I know my beam radius is just the square root of that thing.
And then omega naught is the radius at the beam waist.
It's the beam waist. So once you know the beam waist, you know, everything else about that beam is characterized. So, all right, so all this fell out of this equation. And so I keep pounding on it. We now have Q and Z naught, two good numbers you're going to get to know and love. Let's keep going. So what else can we extract from this equation? Well, okay, one last. Let's look at diffraction. I want to look at the phase term next. But if I look at this, I can actually make an estimate what the diffraction angle of my beam is. And so here it's kind of collimated. Let's go way the heck out here where z is much, much greater than z naught. Can you read that? Probably not. Okay, when z over z naught is much, much bigger than 1, this just becomes, the 1 becomes negligible. And so in this case, then we can say that omega of z is approximately omega naught times z over z naught. So it's just linearly growing, so the beam is spreading. What's the diffraction angle? Well, that's just going to be d omega dz. That's going to be theta diffraction, and that's just going to be omega naught over z naught. What's that? Well, there's z naught. So I've got, this is equal to omega naught over pi omega naught squared over lambda equals lambda over pi omega naught. So that's the angle that this thing is spreading. Of course, that's only half the angle. It's spreading downward as well. So the full diffraction angle is twice that. So we'd say for this model we've come up with, we would say, well, it predicts a diffraction angle of 2 lambda over pi omega naught. And I don't know if you remember, but we came up with that formula earlier. We were talking about diffraction, where we just kind of imposed the uncertainty relationship. And we got a diffraction angle, and it was that number. So this is very reassuring. You know, you've kind of creating some math, trying to pull things out of thin air, and the numbers you're coming up with are consistent with everything we understand about these beams and optics. And so this formula is powerful, it's simple, it's very clean, it's very easy to extract things like diffraction from it. So we know the diffraction angle. And of course this is only true in the condition that we're far away. Near the waist, you know, this beam was coming in. You know, you'd think it was just going to come in and form a focus here, but it doesn't. So it's coming in at some diffraction angle, then it clearly levels off, and then it picks up again. So in the waist, things get kind of parallel, but way out beyond the confocal parameter, again, it's just classic diffraction. Does that make sense? So could you find the diffraction angle from this if you had to? No one's going to commit. All right. So let's see what else we can learn here. So we looked at the real part. We have this term here we haven't begun to think about. So let's take a look at it. What riches are going to be found here? So we have an e to the j times a bunch of stuff. So when you have an e to the j something, times something, who knows? I'm just trying to write a function here. Okay, that has a magnitude of 1. So there's no amplitude at all. This corresponds purely to phase. That's all that does. It just tells you how the phase of the beam is going to change as a function of what? Well, as a function of r and z. And so if we play with this, we can, and we see that the phase of the beam as it propagates is going to be kz plus kz r squared over 2z squared plus z naught squared. So this is just a plane wave. It's just going along, accumulating 2 pi over lambda radians per unit length as it travels along. This depends on, it's got this crazy z over z naught stuff, this is the Q effect, depends on radius. So the phase changes as they go off axis, and it changes parabolically. And so what, if we're to graph this, if I were to look at here's a k vector, here's the z-axis, here's a plane wave just cruising along, here's phase, these are wave fronts. So each of these is a wavelength apart. I pick up 2 pi radians every time I move that distance. If I go off axis though, I pick up some additional phase. And so what that says is my actual phase front kind of looks like this. And then as I go off axis, I pick up more phase. So this is introducing some curvature to my beam. Instead of having a plane wave like I thought, I've got a modified plane wave. Yeah, it's cruising along like that, but there's just a little bit of parabolic additional phase being thrown in. And does that make sense? You think, yeah, of course. We know this beam is spreading, and it's going to get more parabolic or curvature as it goes along, and this term here contributes that. So all I'm going to do is kind of figure out how to write that down in terms of understandable terms. And basically, the analogy you make, if we were to, here's a radius of curvature here. Beam is a radius of curvature. This is a distance z. That's a distance r. Your radius of curvature is just going to be z squared plus r squared. And so we can play with this kind of stuff here. We got z squareds and r squareds and all sorts of stuff going on here. And so if you go through and grind it through, this has the equivalent shape of e to the minus j k r squared over 2 r of z. And r of z is given by z times 1 plus z naught over z squared. So this is just basically rewriting this in terms of a radius of curvature. We can kind of see a radius of curvature from the geometry here. The radius of curvature of the beam looks like that. Again, it depends on z naught and the distance we propagate. So this is another good formula to keep on a piece of paper beside your book when you're doing homework. What's the radius of curvature of a propagating Gaussian beam? It's given by that parameter right there. That's consistent with a spreading beam. So that's what we pulled out of this term here. So it's just a lot of information falling out of this thing. So now we know how the beam spreads, and we know its radius of curvature everywhere as a function of z. So if we look at Q, we just look at Q equals z plus j Z naught. Well, that's handy. You know, like I said, that tells me where the waist is. Or if you have me a beam and you say the beam right here is 100 plus 16J, I know that whichever way, if it's going that way, I know the waist must be 100 centimeters back here, and how big the waist is, because I know Z naught. What if I take 1 over Q? 1 over Q, and I do all this math and stuff, and when you got all this, we got Z over Z naughts and stuff, we had this kind of junk here. 1 over Q, when you get through doing it, is going to be 1 over R of Z minus J times lambda over pi omega squared of Z. So 1 over Q, what's neat about Q is it's complex. It's got a real and imaginary term. So there's 2 pieces of information in it. And when I do the inverse of Q, there's more junk in this room. When I do the inverse of Q, 1 over Q, the real part of 1 over Q is the 1 over the radius. So I know the radius of curvature from the real part of 1 over Q. The imaginary part tells me what the spot size is there. Not back, it tells me exactly what spot size is there. So you come along and you say, here's this beam, and you say it's right here, it's Q equals 100 plus J, whatever. Okay, I know where the waist is, and I can go figure out what the waist size is. But I don't know what the beam is here. But if I take 1 over Q, if I invert that number you gave me, now I know exactly how big the beam is right here, and I know its radius of curvature. So I can get either piece of it, and I could have figured that out. I can go back here and propagate it and figure it. So it's not like there's 2 pieces of information, it's just a different way to compute it. So Q is useful in 2 forms. Just tells me where the waist is and how big it is. Or it tells me locally what the radius of curvature is right at Z and the spot size is right at Z. So you'll see both forms. We'll solve for both forms. You know, we take a cavity, we'll figure out the Q is, or we'll do the 1 over, it depends if I'm trying to figure out where the waist is, you know, I'll do that. If I'm trying to know how big is the waist right here, I'll do the 1 over Q. So they're both tools we'll use in our arsenal. Okay, any questions about this? Yeah.
So the 1 over R of Z term is
Yeah.
the radius at that point? Or
At that point, yeah. So if I've got a beam, you know, cruising along, and let's say here's 0, and I know Q right here. So if you give me Q, it's going to tell me what is this distance Z, and how big is Z naught here. But if you take 1 over Q, God, what a mess. 1 over Q is going to tell me what's the radius of curvature, what's R, and what's this would be 2 omega of Z. So 1 over Q tells me the beam locally. Q tells me back here where the waist is. So and they're effectively equivalent. Once I know one, I can compute the other. So it's not like I'm getting 4 pieces of knowledge out of this. It's just getting it in different forms. All right, so that gets us through that term. We got Q under control now. We solved for it, and then we shook our head and looked at it. We figured out what all the terms mean. Yeah.
So I'm still trying to get the Z and Z naught concept in right now, but then so Z naught is confocal parameters.
Yeah.
And then Z, what exactly is that?
Z is somewhere on this axis. So I've got a laser beam. I shoot it to the moon. So it started here. This is 0, and 186,000 kilometers away. That's Z. You know.
Okay.
Z is my distance along the beam.
Okay. So is it the distance from the start of the
From the waist. From the waist.
Okay.
Yeah. And what's going to get fun is, let's say I run through a lens. I created a new waist. So now there's a new Z over here. There's a new Z equals 0 here.
Okay.
So we'll talk about that. But when Z is where the waist is. And then if I go through a lens, okay, that 0 is different. I've got a new 0.
Okay.
But Z is where the waist is.
Okay.
Or Z equals 0 is where the waist is. Yeah. Okay. All right. How about this P thing? So part of that equation we came up with. How are we doing on time? What do we have? 5? We have 10 minutes? Okay. We had this term P prime of Z was equal to minus J over Q of Z. So that would set that other term equal to 0. So we have to solve that. Well, fortunately, we know Q of Z. So this is minus J over Z plus a constant. So we just integrate with respect to Z. And we find P of Z equals the log of 1 minus J Z over Z naught. Now here's where teaching 2100 pays off. I'm going to write this in terms kind of a phasor notation here. So I can rewrite that as 1 minus J Z over Z naught is the same as 1 plus Z over Z naught squared, the square root, times e to the minus J tan inverse of Z over Z naught. I can write it as a magnitude and a phase, as a magnitude and an angle, because it's a complex number. All we're doing for plotting, I have 1, and I have, here's Z over Z naught, and so I got some angle, and I got some magnitude. So I'm writing this complex number, which is sitting right here. Here's the real imaginary. I'm writing it as a magnitude and a phase and an angle. That's all we're doing.
Should it be D divided by D naught?
Should be Z over Z. Yes. Yeah. Thanks. Yeah.
Is it always going to be represented as Z over Z naught? So like I noticed in the when you wrote R, it was Z naught over Z.
I don't know. I clearly I can make mistakes. I don't know if I did or not.
I just wasn't sure.
Yeah, I'll look. I'll check the formulas. Look in the book. What do the book have? The book has them right, but generally it's usually it kind of comes in this form. You've got Z squared plus Z naught squared, and you got a Z or a Z naught above it. So it's that or it's flipped of that. Yeah. Anyway. Here's this term. We want to take the log of that. And that'll be, because we've got the log of this would be P of Z. And so, and in our solution, yeah, here we go, right here. J times P of Z. So I've got P of Z is here. I'm going to multiply with J, that kind of stuff, and plug that in. So the log, this is that. All right, so where am I going? I'm going in circles here. Oh yeah, okay. I rewrote this in terms of that. So we're going to take the log of this thing, right? The log of that is going to be, so I'll just write that, J P of Z is going to equal to the log of 1 plus Z over Z naught squared minus J times the tan inverse of Z over Z naught. Now I want to take this and plug it into my phase term, my equation up here, and now it will be all done. And so this doesn't look like it means anything at all right now, but I'll explain it in just a moment. So we put that into our final form there, and I'll go to the clean board here, and we get our final expression. So we're going to get E of R and T equals. So this P term, oh God, I forget, E to the J, all this stuff, you stick it in, there's minus signs and stuff. It's gonna, the P term shows up right here. 1 plus Z over Z naught squared to the 1/2. So that comes out of there. Then we're gonna get a E to the minus R squared over omega squared of Z. We're gonna get E to the minus J K Z E to the minus J K R squared over 2R of Z. And then we're going to get an E to the minus J tan inverse of Z over Z naught. Ta-da, we're done. That's the Gaussian beam. Now what the heck does all this mean? Okay, so those are the terms we've come up with so far. Some of these are pretty obvious. This just tells me what the amplitude of the beam is spatially. This is my Gaussian function. Remember, omega squared of z is equal to omega naught times 1 plus z over z naught squared. Okay, so there's my spatial domain. Let me look at this and this. And I'm going to say, you know what? If I multiply the top by omega naught and the bottom by omega naught, I haven't changed anything, have I? So here's omega naught. Here's omega of z. Right? This is just omega of z. So what's happening here? This is very clever. This is where P of z kind of kicks in. As the beam spreads, the electric field has to reduce. It's kind of the 1 over r thing. The electric field is getting spread out more and more, so the magnitude of E must decrease. And so this should be r of z. And so this P term automatically took care of the amplitude kind of being diluted as it spreads. So that's where part of the P term kicks in. It's just the spot size at the waist divided by the spot size at z, and that's just my dilution of E doing the spread. Here's my spatial size. This is just the plane wave phase term. Here's the radius of curvature. Remember, r of z was z times 1 plus, I think I see what you're saying, z naught over z squared. Okay, it was z naught over z squared, yeah. I'm sorry, yeah, I didn't understand what you were asking. We should probably talk about that for a minute. And then here's this other P term. And we'll get to that in just a second. So let's talk about the radius of curvature. It is critical that it's defined this way. If I go to z equals 0, what's the radius of curvature? I get r of 0 equals 0 times 1 plus z over 0 squared. So this one wins the day. What's that equal to? How does infinity sound? What's an infinite radius of curvature? It's a plane wave. So at z equals 0, I have a plane wave. If I go way the heck out, you know, r of z is way, way, way bigger than anything else I know. This equals z times 1 plus z squared over z naught squared. It's a big number. It's approximately z. If I go off to infinity, this approaches infinity. So let this thing go off to infinity, I have a plane wave. So I start with a plane wave, I end with a plane wave. So it must have some curvature in between. And if we look at how the beam goes, here's my waist doing its thing. Right here it's a plane wave. How do I know I'm at a waist? I've got a plane wave. There's always a plane wave at z equals 0. At z equals 0, well, you know, all the phase terms are 0. So if z equals 0, there's a waist. As I start cruising along, I start picking up some curvature. And as I keep going, the curvature starts to get bigger and bigger and bigger. And so I'm again approaching r equals infinity. I start at r equals infinity. I get very curvy up here, and then go back. I gotta get minimum curves. Where is it the highest rate of curvature? So if you do dr dz, and you try and find a max for it, you're going to find the max happens at, want to take a guess? What's a characteristic number we know? Z naught. The maximum curvature occurs at Z naught. You can do this. And the radius of curvature is 2Z naught. So it goes from infinity. When it travels the confocal parameter, it reaches maximum curvature, which is 2Z naught, and then it starts flattening out again as it travels along. So the curvature is completely defined here. Key point here, r equals infinity at z equals 0. You know, that's how I know I've got a waist. Yeah.
So the point is where you have your beam waves.
Yeah.
It's like the most focus,
Yes.
but simultaneously it's where it's a plane wave.
Yep. And that's because they're coming at all these crazy angles, but it's like they came in for the landing. They all just level out right here and start spreading out again. So if I look at it this way, you know, they're coming in like this, they're curvy. So here they're concave, here they're convex. To go from concave to convex, you got to go through flat. Yeah, so it's a very nice continuous process here. Yeah.
So at the beam waist, that's where it levels out. The plane wave.
That's where it's plane wave and minimum. Yeah.
So you said the maximal convex or like the curvature, it occurs at z equals z naught.
Yeah.
So
let's say
then
this
naught
is z.
after
Here's 0 when z equals z naught. So whatever that distance is,
Confocal parameter.
it's the confocal parameter. Z naught comes back. Z naught, it's the universal answer, you know. So I'm flat, or I'm infinite curvature here, maximum curvature at z naught. Then I start getting, you never reach a plane wave again, but you're just slowly getting a larger radius as you go beyond that. All right, we've gone over, but that gives you a snapshot. We'll talk about this one here in a minute. We've got 1 second. All that's going on here, if I had a plane wave doing this thing, I get kz phase as I go along. When the beam is coming in doing this, it picks up a little more phase. Tan inverse of minus infinity over z naught is pi over 2. And z is, we go over there. It picks up, in the beam going down like this, it picks up an additional pi over 2 of phase. And as it expands, it picks up another pi over 2 of phase. So this is a very subtle correction. So instead of being a plane wave, it picks up just a little more phase because it's traveling a little bit further angle. That's all it's doing. So it's just a slight, where the hell is it? Yeah, it's just a slight fix to our longitudinal phase. Very subtle. It plays a role. We'll see it when we mode lock, but anyway. Okay, so that's enough. A lot of definitions today.